In quantum mechanics and particle physics, spin is an intrinsic form of angular momentum carried by elementary particles, composite particles, and atomic nuclei. Spin is one of two types of angular momentum in quantum mechanics, the other being orbital angular momentum. The orbital angular momentum operator is the quantum mechanical counterpart to the classical angular momentum of orbital revolution. It arises when a particle executes a rotating or twisting trajectory. The existence of spin angular momentum is inferred from experiments, such as the Stern-Gerlach experiment, in which particles are observed to possess angular momentum that cannot be accounted for by orbital angular momentum alone. In some ways, spin is like a vector quantity. It has a definite magnitude, and it has a direction. All elementary particles of a given kind have the same magnitude of spin angular momentum, which is indicated by assigning the particle a spin quantum number. The SI unit of spin is the joule second, just as with classical angular momentum. In practice, however, it is written as a multiple of the reduced Planck constant h, usually in natural units, where the h is omitted, resulting in a unitless number. Spin quantum numbers are unitless numbers by definition. When combined with the spin statistics theorem, the spin of electrons results in the Pauli exclusion principle, which in turn underlies the periodic table of chemical elements. Wolfgang Pauli was the first to propose the concept of spin, but he did not name it. In 1925, Ralph Kronig, George Uhlenbeck and Samuel Goldsmith at Leiden University suggested a physical interpretation of particles spinning around their own axis. The mathematical theory was worked out in depth by Pauli in 1927. When Paul Dirac derived his relativistic quantum mechanics in 1928, electron spin was an essential part of it. Quantum number. As the name suggests, spin was originally conceived as the rotation of a particle around some axis. This picture is correct so far as spin obeys the same mathematical laws as quantized angular momenta do. On the other hand, spin has some peculiar properties that distinguish it from orbital angular momenta. Spin quantum numbers may take half-integer values. Although the direction of its spin can be changed, an elementary particle cannot be made to spin faster or slower. The spin of a charged particle is associated with a magnetic dipole moment with a g factor differing from 1. This could only occur classically if the internal charge of the particle were distributed differently from its mass. The conventional definition of the spin quantum number, S, is S equals n2, where n can be any non-negative integer. Hence the allowed values of S are 0, 1/2, 1, 3/2, 2, etc. The value of S for an elementary particle depends only on the type of particle, and cannot be altered in any known way. The spin angular momentum, S, of any physical system is quantized. The allowed values of S are where h is the Planck constant. In contrast, orbital angular momentum can only take on integer values of S, i.e., even-numbered values of n. Fermions and bosons, those particles with half-integer spins, such as 1/2, 3/2, 5/2, are known as fermions, while those particles with integer spins, such as 0, 1, 2, are known as bosons. The two families of particles obey different rules and broadly have different roles in the world around us. A key distinction between the two families is that fermions obey the Pauli exclusion principle, that is, there cannot be two identical fermions simultaneously having the same quantum numbers. In contrast, bosons obey the rules of Bose-Einstein statistics and have no such restriction, so they may bunch together, even if in identical states. Also, composite particles can have spins different from the particles which comprise them. For example, a helium atom can have spin 0 and therefore can behave like a boson even though the quarks and electrons which make it up are all fermions. This has profound practical applications. Quarks and leptons, which make up what is classically known as matter, are all fermions with spin 1/2. The common idea that matter takes up space actually comes from the Pauli exclusion principle acting on these particles to prevent the fermions that make up matter from being in the same quantum state. Further compaction would require electrons to occupy the same energy states, and therefore a kind of pressure acts to resist the fermions being overly close. It is also this pressure which prevents stars collapsing inwardly, and which, when it finally gives way under immense gravitational pressure in a dying massive star, triggers inward collapse and the dramatic explosion into a supernova. Elementary fermions with other spins are not known to exist. As of 2014, elementary particles which are thought of as carrying forces are all bosons with spin 1. They include the photon, which carries the electromagnetic force, the gluon, and the W and Z bosons. The ability of bosons to occupy the same quantum state is used in a laser, which aligns many photons having the same quantum number. Superfluid liquid helium resulting from helium-4 atoms being bosons, and superconductivity where pairs of electrons act as single composite bosons. Elementary bosons with other spins were not historically known to exist, although they have received considerable theoretical treatment and are well established within their respective mainstream theories. In particular, theoreticians have proposed the graviton with spin 2, and the Higgs boson with spin 0. Since 2013, the Higgs boson with spin 0 has been considered proven to exist. It is the first scalar particle known to exist in nature. Theoretical and experimental studies have shown that the spin possessed by elementary particles cannot be explained by postulating that they are made up of even smaller particles rotating about a common center of mass analogous to a classical electron radius, as far as can be presently determined. These elementary particles have no inner structure. The spin of an elementary particle is therefore seen as a truly intrinsic physical property, akin to the particle's electric charge and rest mass. Spin statistics theorem: the proof that particles with half-integer spin obey Fermi-Dirac statistics and the Pauli exclusion principle, and particles with integer spin obey Bose-Einstein statistics, occupy symmetric states, and thus can share quantum states, is known as the spin statistics theorem. The theorem relies on both quantum mechanics and the theory of special relativity, and this connection between spin and statistics has been called one of the most important applications of the special relativity theory. Magnetic moments. Particles with spin can possess a magnetic dipole moment, just like a rotating electrically charged body in classical electrodynamics. These magnetic moments can be experimentally observed in several ways, e.g., by the deflection of particles by inhomogeneous magnetic fields in a Stern-Gerlach experiment, or by measuring the magnetic fields generated by the particles themselves. The intrinsic magnetic moment μ of a spin 1/2 particle with charge q, mass m, and spin angular momentum s, is where the dimensionless quantity gs is called the spin g factor. For exclusively orbital rotations it would be 1. The electron, being a charged elementary particle, possesses a non-zero magnetic moment. One of the triumphs of the theory of quantum electrodynamics is its accurate prediction of the electron g factor, which has been experimentally determined to have the value 2999799768069563780-2.00231930436622, with the digits in parentheses denoting measurement uncertainty in the last two digits at 1 standard deviation. The value of 2 arises from the Dirac equation, a fundamental equation connecting the electron's spin with its electromagnetic properties, and the correction of 6997231930400000000.00231930 arises from the electron's interaction with the surrounding electromagnetic field, including its own field. Composite particles also possess magnetic moments associated with their spin. In particular, the neutron possesses a non-zero magnetic moment despite being electrically neutral. This fact was an early indication that the neutron is not an elementary particle. In fact, it is made up of quarks, which are electrically charged particles. The magnetic moment of the neutron comes from the spins of the individual quarks and their orbital motions. Neutrinos are both elementary and electrically neutral. The minimally extended standard model that takes into account non-zero neutrino masses predicts neutrino magnetic moments if, where the mu are the neutrino magnetic moments, mu are the neutrino masses, and mu b is the Bohr magneton. New physics above the electroweak scale could, however, lead to significantly higher neutrino magnetic moments. It can be shown in a model-independent way that neutrino magnetic moments larger than about 10⁻14 μb are unnatural, because they would also lead to large radiative contributions to the neutrino mass. Since the neutrino masses cannot exceed about 1 electron volt, these radiative corrections must then be assumed to be fine-tuned to cancel out to a large degree. The measurement of neutrino magnetic moments is an active area of research. As of 2001, update. The latest experimental results have put the neutrino magnetic moment at less than 6990120000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 1.2 times the electron's magnetic moment. In ordinary materials, the magnetic dipole moments of individual atoms produce magnetic fields that cancel one another, because each dipole points in a random direction. Ferromagnetic materials below their Curie temperature, however, exhibit magnetic domains in which the atomic dipole moments are locally aligned, producing a macroscopic, non-zero magnetic field from the domain. These are the ordinary magnets with which we are all familiar. In paramagnetic materials, the magnetic dipole moments of individual atoms spontaneously align with an externally applied magnetic field. In diamagnetic materials, on the other hand, the magnetic dipole moments of individual atoms spontaneously align oppositely to any externally applied magnetic field, even if it requires energy to do so. The study of the behavior of such spin models is a thriving area of research in condensed matter physics. For instance, the Ising model describes spins that have only two possible states, up and down, whereas in the Heisenberg model the spin vector is allowed to point in any direction. These models have many interesting properties, which have led to interesting results in the theory of phase transitions. Direction, spin projection, quantum number and multiplicity. In classical mechanics, the angular momentum of a particle possesses not only a magnitude, but also a direction. Quantum mechanical spin also contains information about direction, but in a more subtle form. Quantum mechanics states that the component of angular momentum measured along any direction can only take on the values where c is the spin component along the I-axis, c is the spin projection quantum number along the I-axis, and s is the principal spin quantum number. Conventionally, the direction chosen is the z-axis, where Sz is the spin component along the z-axis. Sz is the spin projection quantum number along the z-axis. One can see that there are 2s plus 1 possible values of Sz. The number 2s plus 1 is the multiplicity of the spin system. For example, there are only two possible values for a spin 1/2 particle. Sz equals plus 1/2 and Sz equals minus 1/2. These correspond to quantum states in which the spin is pointing in the plus z or minus z directions respectively, and are often referred to as spin up and spin down. For a spin 3/2 particle, like a delta baryon, the possible values are plus 3/2, plus 1/2, minus 1/2, minus 3/2. Vector for a given quantum state. One could think of a spin vector whose components are the expectation values of the spin components along each axis, i.e., this vector then would describe the direction in which the spin is pointing, corresponding to the classical concept of the axis of rotation. It turns out that the spin vector is not very useful in actual quantum mechanical calculations, because it cannot be measured directly. Sx, psi and Sz cannot possess simultaneous definite values, because of a quantum uncertainty relation between them. However, for statistically large collections of particles that have been placed in the same pure quantum state, such as through the use of a Stern-Gerlach apparatus, the spin vector does have a well-defined experimental meaning. It specifies the direction in ordinary space in which a subsequent detector must be oriented in order to achieve the maximum possible probability of detecting every particle in the collection. For spin 1/2 particles, this maximum probability drops off smoothly as the angle between the spin vector and the detector increases, until at an angle of 180 degrees, that is, for detectors oriented in the opposite direction to the spin vector, the expectation of detecting particles from the collection reaches a minimum of 0%. As a qualitative concept, the spin vector is often handy because it is easy to picture classically. For instance, quantum mechanical spin can exhibit phenomena analogous to classical gyroscopic effects. For example, one can exert a kind of torque on an electron by putting it in a magnetic field. The result is that the spin vector undergoes precession, just like a classical gyroscope. This phenomenon is known as electron spin resonance. The equivalent behavior of protons in atomic nuclei is used in nuclear magnetic resonance spectroscopy and imaging. Mathematically, quantum mechanical spin states are described by vector-like objects known as spinors. There are subtle differences between the behavior of spinors and vectors under coordinate rotations. For example, rotating a spin 1/2 particle by 360 degrees does not bring it back to the same quantum state, but to the state with the opposite quantum phase. This is detectable, in principle, with interference experiments. To return the particle to its exact original state, one needs a 720-degree rotation. A spin 0 particle can only have a single quantum state, even after torque is applied. Rotating a spin 2 particle 180 degrees can bring it back to the same quantum state, and a spin 4 particle should be rotated 90 degrees to bring it back to the same quantum state. The spin 2 particle can be analogous to a straight stick that looks the same even after it is rotated 180 degrees, and a spin 0 particle can be imagined as a sphere which looks the same after whatever angle it is turned through.